Welcome to the podcast on piecewise defined functions. If we take a look at this first example function, it's a really strange looking shape. It starts off like a straight line as x is going from 1 to 3. Then there's a smooth kind of hump up and it tails off a little bit. And then when you get out here to x equals 7, there's a violent jump up and then a real rapid fall down. And how would you algebraically construct a function like that? Well, I don't have any idea. So what I did instead was I put three separate functions together, and that's called a piecewise definition. And here's the definition over here. It says f of x. Now remember, f of x means y. F of x is equal to 2/3 of x if x is from 0 to 3. Well, the equation y equals 2/3 x, that's the equation of a straight line. So what I'm saying is from 0 to 3 on the x, we've got this straight line, and its slope is 2/3, and there's a straight line with a slope of 2/3. For the second part of definition, I went to a square root function, which we haven't really studied yet, but it is that humped up shape that starts when x equals 3 and ends all the way over at x equals 7. It's this part of the graph right in here. And its definition is y equals the square root of x minus 3 plus 2. And y takes on this value anytime x is between 3 and 7. And then the last one is an upside down parabola. You studied parabola in intermediate algebra. This is an upside down parabola, and the formula for it is given here, and that's the shape that I used from 7 to 10. So that's how I got that very strange shaped graph there. Now, suppose all you had was this piecewise definition, and I asked you to find f of 2. Then you'd have to figure out which one of these three formulas that I have for y you're supposed to use to figure out f of 2. Because if you use the second one, you're going to get a different number than if you use the first one. If you use the third one, you're going to get a different number than the second one. So which one do you pick? Well, since x equals 2, go over to this part and see in which one of these pieces is x2. Well, that would be the first piece, so you would use the first definition, the straight line definition. So I'd write that with empty holes, 2/3 empty hole. And since I want f of 2, I'd put 2 in the empty hole. When you multiply fractions, you multiply straight across, so that would be 4/3. Or if you want it in mixed number form, 1 1/3. Well, let's see if that worked. We come over here to x equals 2, that's right here. We read up, and sure enough, that looks like it's 1 1/3 high. So that makes sense. Let's do the second one, f of 4. Again, you have to decide which one of the three formulas you're going to use for f of 4. Well, in the notation, x is on the inside, so that says the x is the 4. So I come down here and saying, well, in which one of these is x4? And that would be in the second one, because in that one x goes from 3 to 7, and that's where 4 lies. So we're going to use this formula. So I'll say the square root of, and again I'll do it with an empty hole minus 3 plus 2, and I'll put a 4 in the empty hole. Well, 4 minus 3 is 1. Square root of 1 is 1 plus 2 is 3. So that says f of 4 is equal to 3. I come over here to f of 4. I count up 1, 2, 3, and sure enough, when x is 4, y is 3. F of 7, now you've got a conflict. There's a 7 here, there's a 7 here. So which one do you use? Well, in the second one, x can't be 7. But it can be 7 because of the equal to bar in the third one. So you would use the third one. So you would say negative, open, empty hole minus 8 squared plus 5. And then you'd put 7 in the empty hole. 7 minus 8 is negative 1, but when you square that, you get positive 1. But there's a negative in front of it. So again, you go back to negative 1 plus 5 is 4, and sure enough, when you go over to x is 7, you can see that y is 4. And you can finish off f of 10 for yourself. You can see from the graph that you should get f of 10 is 1. Okay, let's try the second one. The second one kind of looks like maybe some pilot's wings or something like that, or at least the top bars of a pilot's wings. And it looks like it's composed of a straight line on the left, a cup shape in the middle, and another straight line on the right. Well, let's take a look at the piecewise definition. Sure enough, y equals negative 1/2 x plus 3, that's the equation of a straight line whose slope is negative. Well, this straight line has going down, so that's a negative slope, so that makes sense. The second part, the x squared, is the cup shape of a parabola, and there it is. And notice that the cup shape started at -2 and went to 2, and that it has this parabola definition exactly from -2 to 2. And then we switch back to a straight line definition, this time with a positive slope of 1/2, and sure enough, when we get to 2, we switch back to a straight line with a positive slope of 1/2. Let's evaluate a couple of these. F of -4, which one of the definitions would we use? Well, -4 is not between -2 and 2, but it is between -6 and -2, so we would use the first. So again, I would write it with empty holes. And the first one was a -1/2. And I want to put in -4, so -1/2 of -4 is +2 plus 3 is 5. Let's check it out. We go over to x is -4. We count up 1, 2, 3, 4, 5. Sure enough, worked out just fine. These work out the same way. You can look and see f of 0 is 0. Look at your graph. 0 would be between -2 and +2, so you'd use the x squared. So you'd say 0 squared is 0. And sure enough, if x is 0, y is 0 right there. So I'll leave those two for you to finish out, and let's go on to the last topic. Now I brought the last topic in. This is called the greatest integer function. It's mentioned in your book. It's a very popular function in math for things which jump up. Instead of moving continuously the way these things do, a greatest integer function makes jumps like that with gaps in it. And this is the symbol for the greatest integer function. It's like two L's that are facing each other with the x in the middle, and the low bar is indicating that you round down. And here's how you define it. F of x, which is the greatest integer function of x, is the greatest integer less than or equal to x. That's what you get when you round down to the next integer. Well, let's see what its graph would look like. The first thing we're evaluating is the greatest integer of 1.5. So we want to round down to the first integer we get less than or equal to 1.5, so that would be 1. So at 1.5 on the x, we get 1 on the y. At 1.9 on the x, again we want to round down to the first integer that's below 1.9, so that would be 1 again. So that point would be on it. If I put 1.2 on there, I'd get the same thing. And even if I put 1, if I wanted the greatest integer of 1, the greatest integer that's less than or equal to 1 is 1 itself. So right here I'd have it. But when I get to 2, the greatest integer less than or equal to 2 is 2. So I jump up. So it's like I don't get a value here. I jump up to here, and I'm going to get all of these values. But when I get over to here, I won't get a value here because the greatest integer of 3 is going to be 3. I'm going to jump up again to here. Now this thing works all the way back. The greatest integer of 0. What's the biggest integer that's less than or equal to 0? Well, it is 0 itself. So you're going to be here. This is going to come out. When you get to 1, it's going to jump up to 1. This is why they call this the step function. It's missing the vertical pieces, but in the horizontal pieces it just looks just like a stair step. Now, this is not considered a piecewise function, even though it is clearly in pieces. The reason they call them piecewise defined is they're referring to functions in which the definition itself is in pieces. Here the definition is not in pieces, just the function is, so this is not considered a piecewise function, and that concludes the podcast.